And our next speaker is Benjamin Broos from Fraunhofer, HHI. And speaking about the first of our codec-based presentations, this will be on versatile video coding, VVC, the standard on the final stretch.
Okay, thanks, Will, for the introduction. And so this is versatile video coding, the next international video coding standard. And interestingly, as a connection to the previous talk by Dan, we worked on a lot of these blocks using neural networks that Dan just mentioned. And also we trained intra-predictors, we trained interpolation filters and all that. And as he mentioned, it requires a lot of memory to store the weights of the networks, and also people wanting to put that in silicon. They crippled our approaches a little bit down to something that is actually implementable. But still, the interesting fact here is what we started, for example, with training intra-predictors to predict samples of a block from neighboring samples using a network. So this is now reduced down to a simple matrix multiplication with weights that are trained using such a network. So this, in this video codec, there is a small piece of so this is just machine learning, but it was motivated and came from a deep neural network approach. So this is already in the next international standard, in a small piece at least. Because, as Dan mentioned, that is very complex, especially if you do not operate on a per picture basis, if you operate on a per block basis, to have networks on a small block of samples, that's a huge storage and bandwidth processing problem. So here I would like to focus for this talk on two basic pillars of this codec. The codec itself is a joint ITUT, VCAC, and ISO-IEC MPEG project. These two standardization bodies also worked together in the past on H.264 AVC or H.265 HEVC. And so the first pillar is the coding efficiency. Of course, always need to be reduced. Here the target was 50% over the predecessor, H.265 HEVC. Of course, well suited for HD, UHD, 8K resolution. We have in types of content 10-bit HDR video. So also the content or the type of video that is distributed and used is also getting better and better. And there we need especially coding efficiency for higher resolutions because there the data rates are really high. Then, as the name suggests, when we came up with that name, versatile video coding, it sounded a little bit odd because in the past, it was always advanced efficiency, high efficiency. So it was also, the stress was on the efficiency. But here we have that efficiency that is set, nothing new. But on the other hand, we focused on versatility. And this means that you have wide support for a wider range of applications. And this goes to screen content, adaptive resolution change or adaptive resolution switching for adaptive streaming applications, and something called independent subpictures for 360 video, region of interest from super resolution video, and so on. And what does that mean? I will lay out in the following. So the coding efficiency here, you see a rough representation of how the efficiency in terms of the quality, given by high quality means high PSNR, and the bit rate that is consumed, given by the bit rate on the x-axis. And you see that for the same objective quality measured by PSNR, all these new standards get less and less bit rate. And the funny thing is here you see that the ITU is pretty straightforward. It's like H.261, H.262, then there was a 3, but 4, 5, and then you can guess what the next number will be, right? MPEG is a little bit thick. I know there's one episode of Big Bang Theory where they discuss PlayStation versus Xbox, and so the one guy is confused because PlayStation is easy, it's 1, 2, 3, and the Xbox was 1 and 360, and it's a little bit like that with the names. So I think it's easy to go by the ITU names, but the common name for that standard is VVC. So from H.265 to H.264, we had a 50% bitrate reduction, roughly. As Yuri also pointed out, it's not for every content. There's very easy content that also looks great on, very, very easy content still looks great on MPEG 2, depending on the resolution. But there is always this demanding content where you need the bitrate reduction. So then, the question is, do we need more efficient video coding still? Because in some scenarios, you can even stick with H.264, but there is still content, demanding content that is not covered or captured well with current video codecs. Think about gaming, artificial content as gaming, which is widely spread. You have billions of people watching streamed video games, and this type of content is not really covered. I will come to that later. From the time of Industrial Revolution, there's the Jeffrens paradox that was related to the consumption of a resource, and that time it was coal. So the efficiency with which a resource is used tend to increase rather than decrease the rate of consumption of that resource. And then we can see that. We all, I guess, are familiar with the reports that the amount of data every 70 up to 80% of the bits in consumer internet are video and so on. So the more accessible video gets by a better compression, the higher the consumption is. Like everyone, instead of photos, sends live photos. That is basically just a video and so on. So the usage of video also increases. And so the target here, again, for the first pillar, coding efficiency, 50% compared to HEVC. And then Dan also laid out that hybrid hybrid video coding block diagram with all the inter-prediction, all that. And all these parts, so VVC is not a completely new codec. It's the same principle. You can also apply that block diagram that Dan showed to this codec, but just all these blocks and different parts of the block has been optimized and squeezed to the last bit. So this is, I won't get into details of all these small little things and which position, which kind of predictor uses and so on. That is where we spend 2 weeks every 3 months in the meetings. But just to give you an idea, so this is almost complete list of new features and tools that are included in VVC to increase the coding efficiency. So overall, there are many small improvements of this classic hybrid video coding design. The thing that you can best show to people is the block partitioning, and here you can see you have a much more flexible block partitioning. You have a lot of narrow partitionings now that you can achieve, and if you take the TV tower from Berlin, you can see that these narrow, long partitions are very well suited to approximate this as an object very well. So that's also the reason why sometimes the syntax describing the partitioning of a video into these blocks that are further than processed using prediction and transform and entropy coding, that these syntax in the bitstream is also very well very well suited to do object recognition and edge detection and that kind of stuff. So in terms of numbers, what do we have here is an overview over the different reference software models. So this is the very slow software that everyone implements its algorithms to show the efficiency during standardization and to verify the coding efficiency of the proposed algorithm. So they started with the version 1.0. After call for proposals and so on, we choose our Fraunhofer software-based, cleaned it up with all these tools that have been in there, and just started with a block partitioning approach. It's called a clean slate approach, and that's why you see the green line represents the bitrate reduction in terms of PSNR compared to the HEVC reference model, the HM. So with that first approach only allowing a more flexible block structures and larger basic processing blocks, you have the first 10%. And from there, we started to evaluate everything that was proposed for that new standard by all these companies, including us. Okay, you proposed an interesting algorithm. Let's take that, evaluate it, and if it's deemed good, also complexity-wise, from people implementing it on silicon, we take it and put it on top. So start with a clean slate and put everything on top. We had a lot of neural network stuff, and some of them, as I already said, even made it after it was stripped down massively to be implementable on silicon. So the other two curves represents the estimate of complexity in terms of runtime increase compared to the HM reference model. So the runtime increase for the encoder, with the gray curve, was roughly a factor of 2.2. So moderate increase of encoder runtime. Decoder was even faster. I guess this is because some of these partitionings had lead to a faster decoding. However, then you see over the versions, so after each meetings, all 3 months, we release a new version, we adopt new tools to the standard, so the efficiency goes up, but also the complexity, like the runtime of the encoder. You add more modes, the encoder needs to check more modes, and so the runtime goes up massively. And there also was a good thing that Dan mentioned in his talk. You could use a neural network to train an encoder to make the right decisions, to not test like 1,000 of modes, just evaluate some features and then just test the best 15 modes. And this would take down this complexity reduction quite significantly. So this is where we are with VTM 5.0. 2 weeks ago, we just finalized the meeting in Gothenburg in Sweden, where VTM 6 will be the outcome. They're still merging stuff into the reference software, but the specification text that I'm editing for that standard, that is already final, because we will send it to MPEG committee draft ballot. That is some ISO procedure to represent the first milestone of that thing being final. And in July next year, this standard is then final. So this is the first step of the ISO approval process for that standard, which also means that feature-wise or coding efficiency-wise, we are still at the coding efficiency pillar, that is pretty much set. So from VTM 5 to 6, what comes out of the next meeting, I expect 2% more, and then I think we cannot expect more. We have a decent increase in encoder runtime, but as I said, there are techniques right now that you can plug in the encoder to reduce the number of checks and decisions. Decoder-wise, it's pretty okay, 1.8% factor compared to HEVC. It's totally okay. People implementing the chips, they can do it. So and decoders should be out not too long after the standard is finalized. Yeah, what is interesting, the other is, I look back at the time when we finalized HEVC, and we did all these, also measured the bitrate reduction in PSNR, and that was exactly about the same ballpark against the previous AVC H.264 reference software. And subjectively, it turned out that the coding efficiency the reduction is higher. So this is what we would expect to happen here again, especially as there are features and coding tools that do not show up in a huge increase in PSNR, but you can perceive it subjectively. And if you're familiar with that, you can see that like a reduction of 1%, you barely see it. But if you see it, then that is quite significant. And there are some tools in that whole VVC set that provide a subjective benefit without showing up as an PSNR-based bitrate reduction. But this is still something we need to confirm, and there will be subjective tests conducted soon to verify that hypothesis. So here, main point here is coding efficiency-wise, we already have a significant bitrate reduction compared to the predecessor. So this thing is covered. I would consider that done. Now, the other thing is I already talked about the decoder. The decoder complexity increase was quite moderate. So we also, with a different team, since the algorithmic part and contributions from our side are now going down, because we are almost at the final stage for that standard, or on the final stretch, as the talk is called. We had another team working on a software implementation for live decoding already. And this is some measurements from our current live decoder. It's still, the standard is not finalized, so the decoder needs to be updated every meeting. However, we already passed the worst case complexity point. So from now on, only the decoder gets only simplified or cleaned up. So there's nothing added that adds complexity. So you could consider this stage or this version of our live decoder as the worst case complexity. And here we did some measurements on HD content, 1080p 60. 10-bit, and we used like a Dell laptop we have in our IT park, and this can use up to 6 threads. And you can see here, the more you increase the threads from 1 thread to 6, the higher the frames per second you can decode. Of course, for lower bit rates, you can decode faster than for higher bit rates, but here even for 4.2 megabits for 1080p 60, 10 bits video, if you use more than 1 thread, this one, you will always achieve more than 60 frames per second on a laptop. And this is, I guess, a good thing. And we're still not done with optimizing that thing. So next step would be UHD. But still now, already for that worst case version of a VVC decoder, you can do 1080p 60, 10 bits on a laptop with 2 threads. And this is what we will, if you're interested and you're at IBC, we will showcase that at our booth. So you're welcome to step by and see that decoder in action, and also current encodings with the VVC reference encoder, which is far away from 60 frames per second, but still, that is the next step to work on. So now, coding efficiency, as I said, pretty much done. We go to the versatility. So versatility, screen content, adaptive streaming with adaptive resolution switching and change, independent sub-pictures for region of interest, extraction. First, screen content coding. As I said, there are applications and types of contents that are increasing, especially Asian companies contributing to the standardization work, who are operating networks, say that like the huge load on their networks just gaming content. And this is, for example, from Tencent, a sequence they contributed for our test set Arena of Valor, a game that is massively played, for example, in China, resolution 1080p 60, and this is the type of content that typically the video coding tools that we have in our current codecs are not optimized for. Dan already mentioned if you use a neural network, it could adapt to the content, right? So if you feed that content, you would have a good codec for that content. But usually we had natural content, camera content in our test set in the development of the past standards. So this was not really covered. We already noticed that for HEVC, so that's why in HEVC there was in version 4 of the standard we had the so-called screen content coding extensions that could code pretty well this type of content. Another type of content is desktop screen sharing, remote desktop content like the slide editing sequence. You have very sharp edges in this thing, so you have different signal characteristics that you need to take care of. So the thing is, HEVC version 4 supports it, but who has an HEVC version 4 decoder in its device? No one. So it's not distributed out there. So that was the main issue, the deployment of that extension of HEVC. So that's why, for the sake of versatility, we decided to put tools that are well suited to code these type of content already in version 1 of VVC. So all the decoders that will be deployed for VVC from the first day on will support that type of content. By supporting, I mean coding efficiently this kind of code. It's supported, it's of course. So then there's another feature that was just like 2 weeks ago, we added that. That's why it's like, expect some more detailed slides in maybe in half a year from now, when I did not have to work 8 days fully to get that standard text ready. And it was just recently decided two weeks ago on the meeting. But I guess it gives you a good outlook of what is possible or what will be possible with VVC when it's finalized next year in July. And the thing called reference picture rescaling, principle-wise, pretty simple. When you have adaptive streaming or the bitrate ladders, you switch resolutions in your, for example, in Dash or whatever. But then for every time you perform a resolution switch, you need to have a separate bit stream, separate coded video sequence, as we call it in the standard. So you cannot make use of the content that was previously coded with a different resolution. So the main benefit or the main coding efficiency benefit in video coding is to make use of previous decoded pictures. So once you break that with a resolution switch, you're losing a lot of these coding efficiency benefit in interprediction, for example. So it would be good to could use the other pictures with a different resolution as a reference to predict current samples. And the solution there is pretty simple. It's not a rocket science, but it needs to be implemented and supported by a standard, of course. And the solution there is just to rescale the reference pictures so they can be referenced. So, for example, if you switch from 1080p to 720p, then you need to scale the 1080p reference pictures down to 720p in order for them to be used in the 720p bit stream. So you do not need closed GOP there anymore. And that was a big issue in the Dash community. That's what I got from my colleagues working in that field. And yeah, so this now, VVC now freshly supports reference picture rescaling. At the moment, just with bilinear filters. to start with, and then we have another meeting cycle to investigate what are the ideal filters. So these are currently under investigation in a core experiment. Yeah, and the current thing is that simple that one participant quotes he could implement that filter with a bottle of wine that evening at the meeting. So the current design is very simple, and we are working on it to make more fancy filters to also improve then the quality or the rescaling. And this, when you further think about it, you have rescalers to be able to scale your reference pictures in different resolutions. Then there's just a very, very small step to spatial scalability, right? So you have the scaling filters in your standard that you can do up and down scaling of pictures. Wouldn't it be tempting to then also have spatial scalability, which was there for years? We had a scalable extension for AVCs called SVC. We had a very simple, high-level syntax-based scalability extension for HEVC, not used because there were extensions, and as I said, only version 1 was deployed for this decoder, and no one was really using it. So currently, we decided that we want to use that also to support spatial scalability, but how the exact design of that will be is still to be figured out until the standard is finalized. So you see, first we check the coding efficiency. And then we have now several meetings to finalize the feature set on terms of versatility. And then next is independent subpictures. The independent subpictures, perfect application would be tiled streaming of 360-degree video. So you have a 360-degree video in an ERP projection format, but then you have another tile here with a much higher resolution of the preferred viewing direction. The thing is, you have a mobile phone or some device on glasses or whatever that has a decoder that can only support 4K decoding. So what you can do, you can throw the whole whatever 8K by something panorama in, scale it down, rescale, and the quality gets messy, or you just have very high resolution at the viewing direction, so you get the best quality where you look at. And if you be able to independently extract this tile from the bit stream, including padding at the boundaries, what you have usually don't only have at picture boundaries. So if you consider that as a sub-picture, and when you extract it, you have padding, and all these features you have at picture boundaries, and that is built in from version 1. That's everyone could use it for tiled streaming from day one that standard is deployed. Okay, so coding efficiency done. We have the bitrate reduction in place. Right now, we're just making some things simpler without losing coding efficiency. Software implementation, we have a live software decoder that is able to decode already HD 10-bit live, and it's just gets simpler. The second part, the versatility, is decided in principle. So we have the concepts we have the applications that we want to support by the VVC standard, and now the details have to be figured out until the standard is final. So coding efficiency in terms of PSNR, we have 36% bitrate reduction for HD and UHD content. Test model for VVC against the test reference software for HEVC. Roughly 10% encoder time decrease, but only 1.8% decoder time increase. And very important, interesting new features to support versatility. Screen content coding, can be, or screen content can be coded very efficiently for gaming, screen sharing. We have a reference picture rescaling filters implemented. Yeah, and independent sub-pictures, and the standard will be final by next year in July. Thank you very much.